There is a component inside a Rolls-Royce jet engine that operates in gas hotter than lava. Not warm gas, not uncomfortably hot gas. Gas that is 400 degrees above the melting point of the metal the component is made from.
Lava, the stuff that swallows houses, reaches about 1300 degrees Celsius. The gas flowing past this component reaches 1700. The metal it's made from melts at 1300.
Today, we're breaking down the technologies that make Rolls-Royce, not the car, the engineering company, genuinely impossible to replace. Jet engines, naval reactors, the next generation of propulsion that will fly your grandchildren. Let's go.
Quick housekeeping. Rolls-Royce motor cars, the £300,000 car with the wool ceiling, is owned by BMW and has nothing to do with what we're talking about today. Same name, different company, completely separate since 2003.
Rolls-Royce Holdings, the one on the London Stock Exchange, has 42,000 employees, £17.8 billion of revenue in 2024, and makes four things: jet engines for aircraft, gas turbines and nuclear reactors for warships and submarines, and power systems for everything from data centres to main battle tanks.
The Royal Navy has operated nuclear submarines since 1963. Every single reactor in every single one of those submarines was designed and built by Rolls-Royce in Derby. 65 years, not one exception.
A jet engine does one thing. It compresses air, burns fuel in it, and extracts the energy to push the aircraft forward. The compressor squeezes the air, going from atmospheric pressure up to 50 times that in the Trent XWB. And then the turbines at the back extract energy from the burning exhaust to drive those exact compressors.
Think of it like this. It's like a series of fans. Fans at the front squeeze air in, and fans at the back pull energy out. Each set of fans is connected by a shaft, like a rotating axle running through the middle of the engine.
Here's the problem with the way everyone else does it. GE Pratt & Whitney, they use two shafts. One shaft carries a big front fan and the low pressure turbine at the back, locked together spinning at the same speed. That's the crucial part. The other shaft carries the high pressure compressor and turbine, also locked together. Two shafts, two speeds.
The issue is that different parts of the engine want to spin at different speeds to be most efficient. The big fan at the front wants to go slowly. The high-pressure compressor wants to spin fast. If they're locked together, you're compromising everything. Nothing is operating at its best. You're flying a compromise.
In 1968, Rolls-Royce did something nobody had done before in a production engine at this scale. They added a third shaft, an intermediate pressure shaft sitting between the LP and HP shafts. Now each shaft, low, intermediate, high, rotate independently at its own optimal speed.
The LP shaft on a Trent XWB runs at 3000 RPM, the IP shaft at 7500 and the HP shaft at 12,000. Three shafts, three different speeds, every component operating at its peak simultaneously. This three-shaft architecture is the direct result of the RB211 engine, the one that bankrupted Rolls-Royce in 1971. The engine that destroyed the company also became the foundation for every large civil engine they've made since. The Trent 700, the Trent 800, the Trent XWB, all three shafts, all descended from that 1968 decision.
Back to the blade that lives inside gas hotter than lava. How? First answer, the way the blade is grown. I use that word deliberately. Grown, not made.
Think of it like this. A metal component is normally like a wall made of bricks. Millions of tiny crystals, called grains, packed together with boundaries between them. Those boundaries are weak points. Under heat and stress, over thousands of hours, cracks start at the boundaries and spread, and components fail.
Now imagine if you could build that same wall, but with one single continuous crystal. No boundaries, nowhere for cracks to start, no stress concentrators. The entire blade is one piece of aligned metal at the atomic level.
That's what Rolls-Royce does. They pour molten nickel superalloy into a blade-shaped ceramic mould. At the base of the mould is a single seed crystal, a tiny piece of pre-aligned metal. The mould is then withdrawn from the furnace at an extraordinarily controlled rate, held to within 0.5 degree Celsius so that the solidification starts at the single seed and propagates upwards through the entire blade, one continuous crystal with every atom aligned in the same direction.
The result, a turbine blade with roughly double the creep resistance of a conventional casting. It can withstand 400 degrees Celsius more than the metal's theoretical melting point, before you even add the second survival mechanism. Even a single crystal blade cannot survive 1700 degrees ambient temperature without help. No material on Earth can. So Rolls-Royce engineers built the blade a cooling system that works while the engine is running, from the inside out.
Think of it like this. Your skin sweating on a hot day. The moisture evaporating off your skin keeps you cooler than the air around you. Scale that up to aerospace engineering and you have what's happening inside the Trent XWB turbine blade right now on aircraft flying all over the world.
In each blade, cast in during manufacture using ceramic cores that are chemically dissolved afterwards, is a network of cooling passages. Some of these channels are thinner than a human hair. Relatively cool air, bled off from the compressor at around 600 degrees, is pumped through these passages continuously while the engine runs.
That air exits through hundreds of tiny holes in the blade's surface, holes drilled or cast with extraordinary precision, and forms a thin protective film of cooler air over the blade's exterior. That film is what stands between the blade metal and the 1700 degree gas stream. It's not touching the blade, it's wearing a jacket of cool air.
Each HP turbine blade in a Trent XWB has approximately 400 individual film cooling holes. Together, they're holding a piece of metal below its melting point inside conditions that should make it liquid.
The engineering to get this right, calculating exactly where every hole goes to provide maximum protection without wasting too much cooling air on blade aerodynamic performance, took decades of computational fluid dynamics and thousands of hours of rig testing. There is no shortcut.
Jet thrust works by pushing air backwards. The more air you push, and the faster you push it, the more thrust you get. But here's the efficiency insight that transformed commercial aviation. It is far more efficient to push a large mass of air slowly than to push a small mass of air very fast. The maths on this is unambiguous.
Think of it like this: swimming. If you cup your hands to push a large volume of water back per stroke, you move more efficiently through the water than if you slice your hands through like blades pushing less water faster. Same physics, same answer.
So engine designers have been making the front fan bigger and bigger, moving more air slower around the outside of the engine core, rather than relying on the hot jet exhaust from the core to do all the work. The bypass ratio tells you how much air bypasses the core compared to how much goes through it.
1950s jet. Bypass ratio 0. All the air went through the core. Very noisy, incredibly thirsty. The Trent XWB, bypass ratio 9.6. For every kilogram of air going through the core, nearly 10 kilograms bypasses it through the fan. That's why modern jets are so much quieter and more fuel efficient than the early ones.
But there's a physical limit. The fan wants to spin slowly. The turbine that drives it wants to spin fast. When they're locked to the same shaft, you can only compromise. Rolls-Royce's Ultrafan solves this with a gearbox.
The Ultrafan power gearbox transmits 100,000 horsepower, the output of 70 Formula One cars, through a box weighing 250 kilograms. Accurate to micron tolerances, the fan runs at 2,500 RPM. The turbines run at 3 times that, both at their optimum simultaneously.
The Ultrafan Demonstrator, a 140-inch fan, the largest jet engine ever built, ran for the first time in Derby in November 2023. It is 25% more fuel efficient than the first generation of Trent engines. It runs on 100% sustainable aviation fuel. It is the future of large civil aviation, and it exists.
This is where Rolls-Royce goes somewhere completely unexpected. The same company that makes the world's most efficient jet engines has also, quietly, been the sole supplier of nuclear reactors to the Royal Navy for 65 years.
A pressurized water reactor works like this. Uranium fuel, enriched beyond civilian reactor specifications, exact levels classified, undergoes controlled nuclear fission in the reactor core, releasing heat. Water is pumped around that core under pressure so extreme, 155 bar, that it cannot boil despite reaching over 300 degrees Celsius. That's 150 times atmospheric pressure. That superheated water passes through a steam generator, heating a second loop of water at lower pressure, which boils normally and drives turbines that spin their propulsion shaft.
Think of it like this: a giant, very controlled kettle, but instead of heating the water with a gas flame, you're heating it with nuclear fission, and instead of the steam making you tea, it drives a submarine through the ocean at 30 plus knots.
A nuclear submarine needs no air. It can remain submerged indefinitely, limited only by food stores and crew endurance. No diesel submarine can come close to that. It is the defining military advantage of nuclear propulsion, and every Royal Navy nuclear submarine has a Rolls-Royce reactor.
The PWR-3 Plus, the latest version, going into Australia's future SSN AUKUS submarines, has 30% fewer parts than its predecessors, a core designed to last the entire 35-year life of the submarine without refuelling, and passive safety systems that cool the reactor without pumps in an emergency. Rolls-Royce is currently doubling the size of its Derby factory to build them.
Everything we've talked about so far, the blade cooling, 3 shafts, the bypass ratio, all of it burns jet fuel, kerosene. And kerosene produces carbon dioxide. Aviation is committed to net zero by 2050. So what does the engine of 2040 run on?
In November 2022, Rolls-Royce ran a jet engine on hydrogen fuel at a Ministry of Defence test facility in the UK. First time a UK jet engine of that scale had ever done it. Hydrogen burns producing water vapour, not CO2. If the hydrogen was produced using renewable energy, the entire fuel cycle is zero carbon.
The engineering challenge is combustion physics. Hydrogen burns approximately 8 times faster than kerosene, and at different temperatures. The combustor, the part of the engine where fuel burns, has to be redesigned from scratch. The flame behaves completely differently, so getting it stable, controlled, and safe across all operating conditions is genuinely hard.
Hydrogen has 3 times the energy of jet fuel by mass, but it's also 4 times bulkier, even when liquefied at minus 253 degrees Celsius. The tank is the problem. The engine, Rolls-Royce is already proving, is solvable.
Single crystal blades that survive conditions that should melt them. 3 shafts each spinning at their own perfect speed. A gearbox the size of a suitcase transmitting the power of 70 Formula 1 cars. Nuclear reactors that power submarines across oceans without ever surfacing. Now, a jet engine that runs on nothing but hydrogen and produces nothing but water.
This is a company that has been at the frontier of human engineering for 120 years, that has gone bankrupt and come back, that powers the planes you flew on last holiday, the submarine defending your country, and if the engineers in Derby have it their way, the zero-carbon aircraft your kids will fly.
If you want the full company story, the founding, the bankruptcy, the AUKUS connection, all of it, the podcast episode linked below is where you want to go. Grilled Atlantic salmon with a garden salad.
If you know someone who studies engineering, works in resources, aviation, defence, or just thinks machines are the most interesting things humans have ever built, send them this video.
And down in the comments, tell us what company or product you want us to pull apart next. We've got a list, but we'd rather build it with you guys. Mining equipment, ship engines, tunnel boring machines, rocket motors, nothing's off the table.
We'll see you in the next one. Sure.